All right, thank you very much, Josie. And thanks for coming, everyone. I'm really excited to be the one who's able to give this seminar series. And before I begin, I just want to give my sincere thanks to both Josie as well as Corin. So I'm the one that's actually giving the seminar. All I really had to do is I had to come up with some topics, make some slides, but Josie and Corin really did all of the logistical work with the registration, handling emails to potential registrants and that sort of thing. So before we begin, I think we should all thank Josie and Corin. All right. So talk a little bit about myself before I begin. So yes, I'm a third-year PhD candidate in biostatistics over in the Department of Epidemiology, Biostatistics, and Occupational Health at McGill University. So up in Purvis Hall on campus, if you've ever been there, at the very top of Peel Street. My supervisor is Dr. Celia Greenwood over at the LDI Center for Clinical Epidemiology. So you may know it, it's over in the H Pavilion. I know until recently, a lot of people didn't even know there was an H Pavilion because it wasn't even connected to the main hospital, but we do exist. So that's where my office is as well, over in epidemiology. And my co-supervisor is Aurélie Lab over at HEC Montréal. So all of my training has been quantitative. It's been in statistics. I did my undergraduate degree in statistics, did my master's degree here at McGill, same department in biostatistics, and now I'm doing my PhD in biostatistics. And I really specialize in the analysis of, not so much the analysis, but the development of statistical methodology for genetic and genomic studies. So my PhD thesis is concerned with the analysis of microbiome data. I've worked in DNA methylation data back in my master's degree, and I still continue to do that today. And I've also worked with RNA-seq data. And I've been involved in genomic studies in a variety of different settings, from autoimmune disease, asthma, colorectal cancer, and I'm currently working on something in anorexia nervosa. So I think I have a unique perspective in that I interact with people both from, kind of a pure math, pure statistical background, and I also interact with scientists and physicians and people who are very much on the wet lab side of things. All right, so this seminar series is meant to give insight into proper implementation of statistical methods in biomedical research. So in my interaction with people outside of statistics, I think that there's kind of a general fear when it comes to doing the statistical analysis of biomedical data. And part of what I hope to do with this is somewhat alleviate that fear. And I say somewhat because, of course, I want that fear to exist a little bit because I wouldn't have a job otherwise. But hopefully I can, enlighten some concepts for you through the course of this seminar series. So this series is meant to be introductory. It's going to be very basic. And the reason I do that is because I don't know what backgrounds everyone's from. I don't know how much statistics people have seen before. So in particular, today's lecture is going to be very basic. I'm going to start with what is statistics, what are population parameters, different types of descriptive statistics. And I'm going to progress a little bit, get a little bit more advanced as we go on. But in general, it's meant to be a very introductory sort of seminar series. And before we begin, I actually just wanted to take a quick poll of who everyone is. So how many people are students? Show of hands. Okay, good amount. How many people are staff, like research associate, research assistant, that sort of thing? Okay. Do we have any health professionals, physicians, nurses? Good, okay. If you're a hospital patient, you're probably in the wrong place. So, okay, good. We have a really good mix of people here. Okay, so I'm going to do my best to focus mostly on biomedical applications, biomedical data. I have several examples today that we're going to see on data from the International Mouse Phenotype Consortium. I have other publicly available data that you can download yourself and practice on if you like. And really the emphasis on these lectures is going to be on proper implementation, making sure you're using the right tests, making sure that you're checking your assumptions, and proper reporting of your results, which is something that is very, very important and often overlooked. And so the good thing is we're not going to go into the math of all these methods too much. Really, we're going to focus on how to implement them and how to interpret them. I'll go into the math a little bit just for the sake of completeness, but you won't have to worry about it too much beyond that. And I'm going to do a little software tutorial. It's going to be very short, like 10-15 minutes at the end of each lecture. So I'm going to do this in SPSS. And the reason we chose this is because it's available for download to all McGill students. So I know some of you might not have access to SPSS. So there is an open source version called PSPP. You see what they did there? They just switched the P's and the S's on that. So that's free to download. And because everything we're doing in this seminar series is going to be very basic, it will all be included in that open source version. So you can download that if you like. And that being said, pretty much any statistical software will include the methods that I'm using in this seminar series. So you don't even have to use SPSS if you don't want to. But anyway, the point is I'm going to do a tutorial at the end of every session, and then we'll post the data online in a short kind of set of instructions. And if you want, you can go download all that and practice on your own. Right, so the last thing I'm going to talk about before I get into the actual lecture is our schedule. So it's going to be the same time. It's always going to be 10 to 12. Even though we have the room booked for 2 hours, I'm going to aim for no longer than an hour and a half, just because I think everyone's going to get a little bit tired if we go any longer than that. So today's really going to be a test run to see how long everything takes. So today I'm going into the intro to biostatistics. Next week we go into hypothesis testing. So I'm going to focus specifically on t-tests, different type of t-tests. On October 2nd, we're going to go into simple and multiple linear regression. This is contrary to what I had originally said in the sample syllabus. I had originally had simple linear regression and one-way ANOVA, but I decided to just put linear regression all into one lecture. Then, as I'm sure you can guess, on Thanksgiving, there's no lecture, so we'll skip a week. And then on the 16th, one-way and factorial ANOVA, and then on October 23rd, just a very general putting it all together. Okay, I have statistical data. What should I do? Where should I begin? And how to report results. Okay, so before I start, does anyone have any questions about kind of the logistics of this whole course? No? And I should also point out that when you ask a question during the seminar, we do have a microphone. So Josie at the front here will be able to give you the microphone, and you can speak in the microphone so that your voice ends up on the recording. So just be aware of that. All right, so why do we need biostatistics? So I often use the terms statistics and biostatistics interchangeably. Really, the bio just means statistics in a very applied setting, in biomedical sciences, in medicine, genetics, genomics, that sort of thing. But at the end of the day, it still is just statistics. So we often have questions that we want to answer through quantitative means. So we do some sort of study, we collect data, we have a lot of quantitative data. If we look at our data in, say, an Excel file, it can be very difficult to discern any patterns just by looking at our raw data. And so statistics allows us to sort of compress our data down into a human readable format and answer very specific questions that we might be interested about. And these days, particularly with new genetic and genomic software, we have, genetic and genomic platforms, we have a huge amount of data available for analysis. And this is true outside of biomedical sciences. In Facebook and Google, they have petabytes and petabytes of data that they need analyzed. And so statistics is becoming very, very important in our society. And lastly, we also need a way to report our results responsibly. As a statistician, I think it's very cool that I get to be involved in the research process right from the beginning, in the study design, right in the middle when it comes to making kind of ad hoc decisions, and afterwards when it comes to doing the analysis and writing up publication. And that reporting part is something that's very, very important, and I will focus on as we get further into the course. Okay, so in statistics, the main quantities that we're interested in examining are what we call population parameters. So population parameter is some sort of numerical quantity that helps us describe some aspect of the distribution of a variable of interest. So for example, a population parameter could be something like the average age of all Canadians. It could be something like the proportion of individuals who are going to vote for a certain candidate in the next election. A population parameter could even be something like a difference in means. So let's say you're looking at blood pressure in an experimental group and a control group. Well, the mean blood pressure in each of those groups, those are parameters, but the difference between those two means is also itself a parameter. Getting a little bit of feedback. We're good now? Okay. Yeah, so the difference between those two means is also itself a population parameter. So in some cases, population parameters can be very abstract things. And the problem is that we don't know the true values of our population parameters. The only way that we could know the true values is if we sampled every single individual in our population. And most of the time, that is either infeasible or impossible. So the point is we use statistics to try to get good estimates instead. So it's common for us to represent population parameters with Greek letters. So for example, we might use the Greek letter mu to represent the average or the arithmetic mean of a variable of interest in a population. We could use sigma to represent the standard deviation of that variable. If you don't remember what standard deviation is, I'll go into it in a few minutes. So the point is that, as I said, collecting data from the entire population is infeasible or impossible, and so when we do experiments and observational studies, we often can only take measurements from a subset of our population. So we call this subset a sample. And everything, all the observed variables that we take from this sample, whether they be qualitative or quantitative, form what we call the data. So the data is just everything that we observe over all of our samples. So if we want to make conclusions from our sample and generalize them to the entire population, well, we have to make sure that our sample adequately resembles the true population. So if I were to take, a poll of everyone in this room, Of course, I can't use that data to generalize to the entire population of Canada because there's a very specific makeup in this room. So that's something that we always have to be conscious about, whether or not what we have in our sample is going to generalize well to some population of interest. So once we have our data and we start to calculate quantities of interest like means, medians, modes, standard deviations, these quantities are referred to as statistics. So this is a very important point. We have a quantity that we calculate from our data is called a statistic, and the equivalent quantity calculated on the entire population is a parameter. It's a very important difference. So yeah, some examples of statistics. If we just take the average of a variable over individuals in our sample, could do the same with the standard deviation, but even things like the maximum and minimum values of a variable in a sample, those are also statistics. And so we use statistics to try to get estimates of the true values of the population parameters. For example, if we took a random sample of Montrealers and asked them who they plan on voting for, well, the proportion that say they're going to vote for candidate A for mayor in the next election is the statistic, and the proportion who actually end up voting for that candidate is the parameter. Another example could be, let's say we're looking at some cross-sectional study and we take the slope of our best fit line between age and blood pressure. Well, so that slope is also itself a statistic, and the corresponding population parameter would be the average increase in blood pressure per additional year of age. So again, that's another one of those more theoretical population parameters. So the point is that whatever we do get from our statistic is almost certainly going to be wrong. It's very unlikely that when we take a mean that it's going to be exactly equal to the mean of the population. But as long as our value that we calculate in our sample is close to the truth and would be close to the truth fairly often if we had taken repeated samples, then we don't really care. All we want is for the statistic to be good enough to be informative, to answer our research question of interest. So there's a very famous quote that gets said all the time in statistics. So this is a statistician, very well-known statistician named George Box, and the quote is, "All models are wrong and some are useful." So every single model that I'm going to show you over the course of this series is going to be wrong, but they can also be very useful. They can help us answer questions about differences between groups. They can help us answer questions on how variables are related to each other, and they're not perfect. If they were perfect, they wouldn't be called models, but we can still do some really, really cool things with statistical modeling. So what should we be concerned about when we're doing a statistical analysis? So yes, we can accept a little bit of error in our estimates, but something we don't want is we don't want to systematically over or underestimate quantities. That's what we call bias. Every statistical test that we use relies on some sort of assumptions, and assumptions which are sometimes unverifiable. It's true that we may have diagnostic tools to be able to check these assumptions, or we could use external knowledge like previous publications to check our assumptions, but sometimes assumptions are just completely ignored. A good example of that is missing data. So let's say you're doing an analysis and you have some individuals who have missing values for the variable of interest. Well, it's common for people to just remove those individuals from consideration. Well, it turns out that if the chances of a person having missing values is related to other variables in other variables that you've collected, then removing those individuals will introduce bias into your analysis. And so as it turns out in that special case, it's better on average to kind of impute best guess values for those missing values rather than remove those people from the population. So, but in practice, often people don't even consider that situation and they just get rid of everyone with a missing value without considering the consequences of that. And that's something that even I'm guilty of. So unfortunately, we don't have time to get into missing data in this lecture series. I wish we did, but we'll do what we can. And so lastly, we have to make sure that we're performing the right statistical test and that we formulate our parameters in a way that's actually answering the research question of interest. All right, so first I'm going to talk about investigating a single variable, investigating the distribution of a single variable. Any questions so far? Okay, so when we collect data, so we're talking about one variable, of course not every single individual in our sample is going to have the same value of that variable. It's going to differ over our individuals. So that's going to form a statistical distribution. And how we visualize that distribution depends on what kind of data we have. So our two main kinds of data are, first one is categorical data. That's a subset of something we call discrete data. With categorical data, you just have a small number of categories, and each individual can only fall into one of the categories. So in that case, we can often use a table to summarize the counts or the percentages of individuals in each of those categories, or we can use things like pie charts, bar charts, that sort of thing. So some examples of purely categorical variables are sex, a disease case versus control, race, neighborhood, things like that. There's a special kind of categorical variable that we call ordinal variables. So these are categorical variables that actually have some sort of natural ordering. So if you're doing a survey and taking self-reported health, and the choices are poor, good, and excellent, well, that has a natural ordering. Poor is kind of like the worst, good is in the middle, and excellent is at the top. Same with level of education, high school, university, grad school, that sort of thing. So when we analyze ordinal data, we can usually do kind of a slightly different sort of analysis than we would do with purely categorical data. So on the other end, we have continuous data. So continuous data is just data that's a number. So examples are age, height, weight, cell count per unit volume of blood. And with continuous data, it's a little bit harder to visualize, but it's not too difficult. We use what we call a histogram, which I'm sure most people are quite familiar with already. So here's an example of a histogram. So this is data on mouse weight in grams that I took from the International Mouse Phenotyping Consortium. It's a great website, publicly available data, tons and tons of data on mouse phenotypes and genotypes as well. So the point of the histogram is that we formulate these bins, and each of these bins represents some interval, and the height of each of these bars represents the number of individuals that fall within that bin. So if we're looking at 20 grams to maybe 21 grams, 22 grams, something like that, we go up and we see, okay, there's about maybe 130, 140 individuals falling within 20 and 22 grams. And so histograms are very good for getting a general idea of the shape of the distribution of the variable of interest. So one thing you can do with histograms is you can change the size of those bins. So what I've done here is I've made it so that each of the bins is just a little bit smaller, and instantly you can see that the histogram looks a lot different than it did before. So every time you shrink the bins in the histogram, you're going to get a little bit more detail in the total distribution that you're considering. But you do have to be careful when doing that, because if you shrink the values of the bins too much, then you're basically going to end up with a completely uninformative histogram. You're going to end up with each individual in their own bin. So yeah, and by changing this bin width, I see a little bit more detail. So before I saw kind of a single high point in the histogram, and now I have 2 high points, or maybe even 3 sort of high points in my histogram. And so that does indeed represent 2 separate sort of subgroups. So I've specifically colored them here. I'm sure people can tell me what these 2 subgroups are. Someone just want to yell out the answer? What's that? Yes, exactly. Kind of obvious because of the colors I used, right? So yeah, this shows you right away that just by looking at this histogram, we see, because there's 2 peaks in this histogram, maybe there are 2 subpopulations, and indeed we have male mice with a higher average body weight and female mice with a lower average body weight. So this just goes to show that when you start a statistical analysis, it's good to kind of do these histograms and look at descriptive statistics and just do a general sort of data exploration every time you start a study, and you can find things that you might not have otherwise considered. All right, so that's how you look at, that's how you visually look at the shape of a distribution, but we also have things called descriptive statistics that are going to describe the distribution of our sample. So they fall into 4 kind of distinct categories. One is frequency, so just counts and proportions of different categorical variables. Second one is, these ones are usually what we're interested in our research questions, measures of central tendency. So our means, our medians, and modes. These give us an idea of the center of our data, or kind of like a typical value of a datum. And we also have positional statistics, so maximum, minimum, percentile. They tell us how different observations fall in relation to one another. And finally, we have measures of variation and dispersion, so like our variance and our standard deviation. And these are going to give us an idea of how spread out our data are. This is something that's very important. Usually these are things that are kind of overlooked, but they're going to be absolutely essential when it comes to doing statistical testing further down the road. So first, I'm going to focus on our measures of central tendency. So the first one, everyone here has already heard about it. Everyone knows what this is, but I'm going to just go through it anyway for the sake of completeness. So we have the arithmetic mean, or also known as just the mean or the average. So this is something that's incredibly common. We use it all the time. It's got really nice mathematical properties. It's related to our normal bell curve distribution. It's just a really wonderful thing. Before I define the mean, I'm just going to go into some notation that I'm going to use consistently throughout the series. So I'm going to say that my sample size, so the number of individuals that I'm studying, is little n. I'm going to say that x1, x2, all the way up to xn are just the observed values of a variable over all these individuals. And for shorthand, I'm going to call x without a subscript to just be that whole collection of values. So I think of x as just being the data. So our sample mean, which we call x bar, Again, this is a notation that we use very often. And anytime we have a letter and we put a bar over it, we just mean, okay, we're taking the mean of all the observations for that variable. So x bar is just taking the sum of all the variables, of all the observed values of the variables, and dividing by the total number of individuals. So this is a very intuitive measure. One interesting thing about the mean is that it does consider every single observation. It considers every single individual in its calculation. And by dividing by n, you can think of that n as being distributed, like a 1 divided by n distributed to each one of those observations. And so we're kind of giving equal weight to every single observation. That's what the sample mean is doing. So if we go back to our mouse weight data, I plotted the mean with just a vertical red line. So as you can see, it sort of falls right in the middle of the data. But you have to be careful because we usually think of the mean as being sort of a typical value. But in this case, that's definitely not true because of those two subpopulations, the male mice and the female mice. So if you just throw everyone together into one distribution, well, the mean does not represent a typical value for anyone. So these are the sorts of things you have to be careful about when you're doing statistics. That goes back to the interpretation element I was talking about earlier. So our second measure of interest is the median. So the median is the value that splits our data into two parts of equal size, an upper half and a lower half. And so again, that's another very intuitive measure. And it's very easy to calculate as well. So to calculate our sample median, it depends on whether or not we have an odd number of observations or an even number of observations. So if we have an odd number of observations, well, we take all of our data, we put it in ascending order or descending order, and we basically just take the middle value. Very easy to do. So in this case, I have 7 different observations. And so I just take the fourth one, the one in the very middle, so our median is 56. And if we have an even number of observations, well, obviously there's no middle value in that case. So in that case, we just take the middle 2 observations and we take the average of them. And we just do that by convention. So that is still going to split our data into an upper half and a lower half. So I've also plotted the median on here as a vertical blue line. And as you can see, it falls a little bit to the left of our mean. So yeah, that is splitting that is choosing the exact value that splits 50% of our data to the left of the mean and of the median, and 50% of our data to the right of the median. So the last measure, I forgot about this. Right. So with the median is generally very robust to what we call outliers, or uncharacteristically high or low values, then is the mean. So with the mean, I'll give you an example here. We have a data set with a bunch of observations. So if I were to calculate the mean x bar, we get 46.86. And if we calculate the median, we have 56, as we did before. Now, if I take these top 2 observations, 71 and 86, and bump them up, so now they're 109 and 172, then we calculate the mean again, and we get 64.57, so quite a bit higher than what we had before. But our median is still 56. So I could have made those values as high as I wanted. I could have put them into the billions, trillions, whatever I wanted, and because 56 is still the middle number, it is still the median, no matter what we do. So yeah, Median is a lot more robust to outliers. I've kind of illustrated this on our mouse weight data again. So on the left side here, this distribution is the same data that I was showing before. But on the right side here, between 30 and 50, I randomly simulated just a bunch of values to give kind of this tail to the distribution. And as you can see, so median is more or less where it was before, around 25. And the mean has been pulled quite a bit over to the right. So this is an extreme example of what we call a skewed distribution, specifically a distribution that's skewed to the right because we have this long tail on the right side. And so when you see a mean that's very, very different from the median, that's usually an indication that your distribution is skewed one way or the other. So our last measure of central tendency is what we call the mode. So again, it's quite easy to calculate. So basically, we just take the most common value in our data. So if we have this data set, as you can see in this case, we have repeated measures. Not repeated measures, just repeated values over different individuals. So you can put all of your data into this frequency table. So on the left side, we have the actual values, and on the right column, we have the frequency of each of these values in our data. And so we just choose the highest frequency. So highest frequency is 4, which corresponds to 20. So our mode is 20. That's our most common value. So in this case, the mode was easy because we have these repeated values. But with most continuous data, we're not going to have any repeated values whatsoever. That's especially true when you have data that has many decimal points. And so one way we can find the mode is just by plotting that histogram and sort of visually seeing where our mode is. So in this case, we would just look at the highest point on the histogram, and we look at the corresponding value on the horizontal axis. So in this case, our mode is at 22 grams. There's also ways to sort of numerically estimate the mode in that case, but you know, in this example, it's just very simple to look at the histogram, and you can tell right away that the mode is at 22 grams. All right, so we also have what we call measures of variation. So our measures of central tendency, even though they're usually the main quantities that we're interested in studying, measures of central tendency are very important because they also describe how spread out our distribution of values is. So if you imagine two different distributions, both of them have a mean at 25, but the first distribution varies between 15 and 40, and the second distribution varies between 0 and 100. Well, even though they have the same mean, those two distributions are very, very different. And so this illustrates why we need some measure of variation. And so these are going to become critical when we go into statistical testing procedures like the t-tests and linear regression and all that. All right, so to illustrate how we formulate our measures of variation, I'm going to start with this simple data set. So we only have 5 observations ranging from 1.33 to 8.25. And so I've just plotted them on the right side here. So the horizontal axis there's no quantity on the horizontal axis. It's just the first observation, second observation, et cetera, et cetera. And the value of the vertical axis is the observed value of each of these observations. And so as you can see, we have a pretty good spread on this data. So the first thing we could do is we could fit a mean. We could find the mean of this data set. And so that's going to be represented by this green line. So it kind of falls, you know, somewhat in the middle. So now, how are we going to measure our variation? Well, we tend to measure variation of a variable with respect to how far it is away from the mean. So what we can do is we can calculate the difference between each individual point and the mean. So if a point falls below the mean, then that means it's going to give us a negative value, and if the point falls above the mean, that means we're going to get a positive value. So we call these the residuals. So this is an example of a very, very simple, in fact, probably the most simple statistical model that you could come up with. And one recurring theme that you're going to see is every statistical model can be written as, okay, you have your outcome, or the variable of interest can be expressed as some sort of like explained part of the model plus some leftover stuff, some error that we can't account for. And we're going to always look at this theme of sort of signal to noise. So we're going to look at, okay, how much variance in our data can be explained by our model versus how much cannot be explained. And that's going to go into determining whether or not our results are significant or not. Okay, so we have our residuals. We have the difference between the mean and the observed values. So we want to get this down to a single measure of variation. So as it turns out, if I take the mean of all these values, that's going to add up to 0. So if you calculate that, you'll see that that's true. And in fact, that is always going to be true. If you have a variable, a data set, and you calculate the mean, look at these residuals and add them up, it's always going to be exactly 0. So it's a good place to start, but it didn't really work out for us. So maybe instead of just adding up the values, maybe we don't care if the values are positive or negative. We just care about the actual distance from the point, the observed point, to the mean. So in that case, we would just drop all our negative signs. So take the absolute value of all the observations, and then take the mean of these absolute residuals as we did before. Okay, so now we get something that is not 0. In this case, we get a value of 2.2. So that's a good intuitive value. If it's bigger, it means that our points are very far away from the mean, and if it's smaller, it means our points are very concentrated around the mean. But as it turns out, this value is very, very difficult to work with mathematically. Anyone who's done calculus knows that working with absolute values is kind of a pain in the backside. So we tend to not use this measure as intuitive as it is. So an alternative, we could, instead of taking the absolute value of each of these observations, we can square the values of each of the observations. So of course, if you square a value, it doesn't matter if it's a negative or positive, you're still going to get a positive value back, so we don't have to worry about things adding up to 0. So we take the square of each of those values, take the mean as we did before, so in this case dividing by our number of observations, 5, and here we get our observed value, our value 6.15. So even though this value is a little bit less intuitive, it's not on the same unit as the variable we're interested in studying, but as it turns out, it's very convenient to work with mathematically and is a quantity that's related to a lot of statistical distributions out there. So this is what we tend to use, this sort of average squared error. So this brings us to our first statistic of variation, which we call the sample variance. The sample variance, which we denote by s squared, measures this average squared distance between each point and the mean. So as we did before, we calculate our mean x bar. We take the difference between each of the values and x bar, square them, and be careful, in this case, we're going to divide by the sample size minus 1, by n minus 1. So before we were dividing by the sample size, by the sample size, and this time we're dividing by the sample size minus 1. And the reason we do that is just because we have some error associated with estimating this x bar itself. And so as it turns out, dividing by n minus 1 instead of n means that we get a slightly better estimate of the true population variance. Though admittedly, once you have a big enough n, it's not going to make any difference whatsoever if you divide by n or n minus 1. You know, if you're thinking of a sample size of 1,000, doesn't matter if you're dividing by 1,000 or 999, you essentially get the same variance. And of course, when we use statistical software, it's going to take care of that problem for us anyway. So this is, as I said, very important quantity in statistics. The interpretation, well, a small value means that all your points are very concentrated around the mean, and a large value means your points are very far away from the mean. But the one problem we have with the residuals that I mentioned was that we don't know how to relate the magnitude of the variance to the original observations. We took the square of each of those residuals, so now we're on a different scale from the original units that our data was measured on. So instead of looking at the variance, often what we do is we look at what's called the standard deviation. So with the standard deviation, we basically just take the square root of the sample variance. So by doing that, we actually get the values back to the original units of measurement. So if your original variables were in grams, then the standard deviation is also going to be interpreted in grams. If your variable was kilometers, then the standard deviation will also be interpreted in terms of kilometers. So in publications and stuff, we tend to report the standard deviation, and the variance is something that we save for our calculations. And again, same interpretation as the variance. Small value means very concentrated around the mean, and a large value means very spread out. All right, so we have a number of descriptive statistics. And so we're going to use them to formulate the most famous statistical distribution, which is called the normal distribution, which I'm sure everybody recognizes. So our normal distribution is, if you imagine one of our histograms where we kind of draw an outline around the histogram, the normal distribution is something that tends to appear in nature. I guess it's a very general bell-shaped curve that appears in nature, and a normal distribution happens to have this bell shape. And it's defined by two parameters. The first is the mean, which we call mu. So the mean is going to shift the normal distribution to the left or the right. So if we have mean at 0 represented by this red curve, it's centered right around 0. In this purple curve, the mean is at -2, so it's shifted over to -2. But the mean isn't going to change the shape or sort of the width of that normal distribution. The second parameter is actually the standard deviation of this normal distribution, and that is going to change the shape of the distribution. So small standard deviation represented by the red is very concentrated around 0, and a larger standard deviation represented by the blue curve means it's going to be very spread out. And going back to the start of the lecture, these two quantities, mu and sigma, are population quantities. So these are not statistics, these are population quantities or parameters. So the cool thing about the normal distribution is that our mean, our median, and our mode are all the same. They're all equal exactly to mu. And it's well documented the different percentages of individuals that fall into the different regions of our normal distribution. So if you, and the cool thing about the normal distribution is that you can easily express how many people fall into different regions of the distribution based on the standard deviation. So as you can see here, I have our normal distribution plotted as before. We have mean, median, mode at 0. And over here we have 1 standard deviation to the right, 2 standard deviations to the right, et cetera, et cetera. And over here we have 1 standard deviation to the left, 2 standard deviations to the left, et cetera, et cetera. And as it turns out, if you look at 1 standard deviation in either direction, that's going to contain about 68% of all the individuals. And if you look at 2 standard deviations in either direction of the mean, that's going to contain the vast majority of the individuals in this sample. It's going to, in this population. So it's going to contain around 95% of all individuals in this population. So the cool thing about this is even if you don't have a normal distribution, you can still use that 2 standard deviation rule to kind of get an idea of how spread out your data is. So if you're looking at a publication and there's a table with summary statistics at the very top of the publication, and you see, say blood pressure has a mean of 110 and a standard deviation of 10, well, just based on that, if you assume that you don't have too weird a distribution, it doesn't have to be exactly normal, but as long as you don't have some weirdly shaped distribution, then you can say, okay, 1 standard deviation away from the mean goes from 100 to 120, so we know that a good chunk of people will fall into that range. If we go 2 standard deviations in either direction, we're talking 90 to 130. And so you know that the vast majority of people in this sample should have a blood pressure within that range. So yeah, it's just a very good general rule of thumb that you can use, even if you don't necessarily know whether or not you have a normal distribution. If you think that your distribution is somewhat reasonable, then you can kind of use that rule. Okay, the last thing I'm going to get into is how to compare 2 different variables. Everything now is just concerning 1 variable. Any questions so far about what I've talked about? Can you just wait for the microphone? Thanks.
So you spoke about mean and median. In publications, I only see means usually, but I do get data that seem to have a skewed distribution. So at what point is median a better reflection of your data, and when is mean more appropriate?
So I would say that neither is more appropriate. Really, you need both.
Okay.
So the mean and the median, they both have advantages and disadvantages. So the median has the advantage that it's not very sensitive to outliers, but the mean has an advantage that it does take into account the actual values of every single individual, and sometimes that's what you're interested in. Also, if you're doing statistical tests like your t-tests, that automatically involves the mean, and so it would just make more sense for you to report the mean in that case. But yeah, so it's not really one or the other, really you should always be looking at both. Yeah. Yes? Another question over there.
Thank you. About the histograms and binning, how do you choose how many bins to make depending on how large your data is?
So that's a good question. There's really no set rule. It's just something that you have to play around with and visually decide whether or not you think it's a reasonable bin width. Yeah, and that's something that can be a little bit tricky sometimes, but there's really no rule for doing that.
So I'm actually going to add a question too. I was going to say to Leanne. Hello? Okay. So you talked about sample sizes through all of this, but are you either today or maybe later on going to get into the what an appropriate sample size is? If you talked about over versus under representation, and
Yeah, so I think really in the last lecture, I'm going to go more into sample size and that maybe a simple sample size calculation. I haven't decided everything that's going to go into that one yet, but yeah. Okay, so I'll move on to the last part, and then I'll quickly get into the tutorial, and then we'll have another question and answer period at the very end. So yeah, I'm going to go into some graphical methods for comparing two variables. So of course, most research questions that we're interested in, well, maybe not most, but a lot of research questions are interested in how the distribution of one variable changes in relation to another variable. And there are a lot of statistical tests that exist to study these relationships. We'll get to these later on, but for now I'm just going to focus on graphical comparison. So the first one is what's called a box and whisker plot. This is a term that I don't really use. I just usually call it a box plot. A box and whisker plot sounds very old-fashioned to me, so usually people just call this a box plot. So this is a simple type of plot that allows us to compare the distribution of some continuous variable with respect to the levels of one or more categorical variables. And the different elements on the box plot, which I'm going to show you, show how the data points are spread out in relation to each other, and also it individually plots any outliers. So on the top here we have sort of the format of our box plot. Here the arms are going out sideways. Usually you see this kind of turned 90 degrees, so the arms go up and down. So the variable that the continuous variable that you're interested in studying is on the y-axis. So we have this box. In the middle of the box we have a kind of a solid line, which is the median of our distribution. The box extends out to what we call the first quartile and the third quartile. So the first quartile just means that, okay, 1/4 of the data falls below this quartile. And the third quartile means that 75% of the data falls below that value. So basically, 50% of your observed data is going to fall within this box, and 50% of the data is going to fall outside of the box. And we also have what we call these upper and lower fences. They're based on what we call the interquartile range. Don't really have to worry about how those are formulated, but they just give you kind of an idea of the reasonable spread, how spread out those sort of those tails of the distribution are. And what's not shown here is often if you have outliers, they will separately plot those outliers as individual points on the outside of this box plot. So I'm just going to give a quick example. So we have, this is the International Mouse Phenotyping Consortium data again. So we have two sort of gene types. We have the gene IL-13. So we have the wild type, so just the most common form of that gene in mice. And we have mice with this IL-13 gene where it's been knocked out, where it's no longer functional. And we're looking at on the y-axis the measured value of HDL cholesterol. And then on the x-axis, you can just ignore that was just the date that measurements were taken. So yeah, the orange is the wild type, and the teal is the knocked out gene. And so it's a little bit difficult to tell based on a plot like this what the differences between these two distributions are. Maybe the knocked out mice have a higher HDL cholesterol on average. It's really hard to say. But the moment we put this into a box plot, the answer becomes very obvious. So as we can see, we split this up by male and female as well. So it looks like in female, the medians are pretty similar, but we see a lot less variation within the knockout mice. And in the males, we see a lot more variation in general for the males. And in the knockout mice, for the males, it looks like we have a higher mean or median. It's difficult to actually say whether or not this change is significant. So that's where our statistical testing comes in. But really, when you compare looking at something like this to something like this, you can see that the difference is night and day. Here you can instantly see the differences in distribution. Now you do have to be a little bit careful when you're looking at box plots because they can conceal the data a little bit. So let's say, here I made two almost identical box plots for two different groups. But if I superimpose the true data over this, I get two very different distributions. In this one, I have 100 observations, very much spread out. And this is a very artificial example that I set up. But as you can see, we only have 5 points. And so this goes back to the comment earlier about whether or not to look at, mean and median. This is the same sort of thing. You shouldn't only look at one type of plot. You shouldn't only calculate one type of statistic. You should really do a thorough data exploration before you undertake your analysis, because oftentimes you can find things that you would have missed otherwise. Okay, the last plot I'm going to talk about is the scatter plot. Very familiar plot. So this is what we look at if we want to look at the relationship between two continuous variables. So it's very commonly used with a best fit line. When we get to linear regression in the third lecture, we'll see more of these. So here on the horizontal axis, I have, so this is data from the multi-center AIDS cohort study. And on the horizontal axis, we have baseline HIV viral load, so HIV viral load at the very start of recruitment. And on the vertical axis, we have average change in CD4 count over the course of their follow-up. And these were just two variables that I happened to have available to me. So I decided to plot them together. And as you can see, we can study the relationship or kind of a general trend of these data based on this graph. And I plotted a best fit line. But one thing that's interesting here is that there is a very large spread of the different values of baseline HIV viral load. So we're down around close to 0, and we go all the way up to over 1 million. So as you're going to see when we get into linear regression, when you have values like this one over here that are very far away from the rest of the data, those points tend to be very influential on the slope of this best fit line. And so one thing we can do in this case, and this is something that is used very often, is we can transform our variables. So the most common one, and the one that you should all probably know, is the logarithmic transformation. That's one that we use if our data spans many orders of magnitude. So it's might go from 0 through hundreds, through thousands, through hundreds of thousands, through millions, and it's not uniformly distributed among those orders of magnitude. So I'm going to take the base 10 logarithm of the horizontal axis. So in this case, 3 means 3 zeros, so 1,000, 10,000, 100,000, 1 million. And as you can see already right away, this looks like something that is a lot more reasonably expressed as a line. So that's just something that we're going to get into, but my point here was that sometimes when you have a variable directly from your data, you might want to consider transforming that variable before working on it, because sometimes it can make your life a lot easier. Okay, so what's my take-home message from this lecture? Well, remember, everything that we do is subject to error and potentially bias, so that's something that we always have to be aware about. You have to think about your population that you're studying, and before you do any generalization to your population, you have to really think about whether your sample is representative of that population. always, this is so important, do thorough data exploration before you do any formal statistical testing. You know, what I was doing with those histograms, calculate your descriptive statistics, means, medians, modes, variances, that sort of thing. Because you never know what you might find. You might find something else interesting to study that you hadn't considered before. And also, you want to be able to properly interpret the values that you calculate. All right, so before we get onto the tutorial, are there any questions about the lecture? So the way we're going to do this is, so this is going to be pretty quick. This is going to be 10-15 minutes. And I'm going to do it on my personal laptop in SPSS, and I'm going to try to record it on my own laptop here. Okay. I think I have to open it again.
Oh, yeah? Okay. Okay, go ahead.
Okay, thanks. Okay, so here I have SPSS open, and I just have a general publicly available data set from an R statistical package. So it's just a data set on women with diabetes, a bunch of different variables. So there's two sort of windows or views that we have in SPSS. So the first one is what we call the data view. It looks very much like what you would see in Excel. You see the different variables as columns, and the different rows are the different individuals. If you go to the bottom, you can switch over to the variable view, and that's going to give you more information on each of your variables. So on the left side here, you have the variable name, so that's just like a short sort of name for each variable, a convenient name. And you also have a label, which is going to give you a more descriptive title for each variable. So you can see here we have plasma glucose concentration, blood pressure, triceps skin fold thickness, pedigree, whether or not they're diabetic, BMI as a categorized into lower or higher BMI. Just I think I changed that to be below the mean of below the median of the group and above the median of the group. We have age category and number of pregnancies up to that point. So yeah, this is just a good way you can get a quick summary of all the types of variables that you have. You can look at the potential values by clicking on a button that appears in the values column. It'll give you the different possible values you have for each of your variables. You also have the type of variable. So here we have scale, so that's just like a continuous variable. We have a nominal variable, that's a categorical variable, and then an ordinal variable, that's, as I described earlier, a very specific type of categorical variable where we have a natural ordering. All right, so once you have all your data into your SPSS file or whatever software you're using, it usually tends to be very easy to run these different types of things. And one thing that you'll find out is that when you're doing these analyses, the really hard part actually turns out to be getting your data into this format as it is currently, in this in this sort of very clean format. The data cleaning step is always something that I think people underestimate how much time it takes. Like, I could spend maybe even like a week just getting data into a clean sort of format, because often when I receive data from collaborators, there might be typos, there might be inconsistencies and that sort of thing. So yeah, turns out that once you know how to do these analyses, that turns out to be the easy part, and the data cleaning is often the hardest part of the whole process. But so in order to get descriptive statistics, so most of what you run in SPSS is going to be through this tab at the top called Analyze. So you go to Descriptive Statistics and Descriptives. Again, I'm going to post online at some point more detailed instructions of this, and this recording is going to appear as well, so you can rewatch this if you want. So descriptives. And the way things work in SPSS is usually you have kind of two boxes. You have a list of all your possible variables, and you have a box on the right side which is where you will put the variables that you're interested in analyzing. So in this case, let's say I'm interested in analyzing or looking at descriptive statistics for plasma glucose concentration. So all I do is I highlight that and move that over to that right box. And usually there's a button on the right side for most functions called Options. If you click on that, you can just choose all your different options. So I have mean, standard deviation, minimum, maximum. I'm also gonna look at variance. You just press continue, and then once you have everything set up the way you want it, you just press OK. And it's going to open up this new window, which is called the output window. So this is where all your tables and your plots and histograms are going to appear. So as you can see, that was pretty simple. It automatically gives you your sample size of 200, gives you the minimum value, which is 56, the maximum, which is 199, gives you your mean, gives you your standard deviation of 31, and it gives you the variance. And already you can see why standard deviation is so much more interpretable than variance, because standard deviation is 31. So in relation to the mean, you can picture how wide the distribution of this data is already, whereas with variance it's 1,002. Who knows what that means, really? All right, so I'll show you a few simple graphs. So in order to make graphs, most of what you do is going to be in this Graphs tab, and you can go to the first option, which is called Chart Builder. And the way this works, so let's say I want to do a histogram. I will go to the bottom here and select histogram. They have 4 different types, and whichever one you want, you just click on it and drag it up into this white area. And that's going to set things up for a histogram. And then you take any variables that you want and you just drag them to whichever axis you want the variable to be on. So in a histogram, there's no y-axis, it's just frequency. So we just need to put something on the x-axis. So let's do plasma glucose concentration again. Okay, so have that. And from there, it's as simple as just pressing OK. It's going to take a second to plot this. And there's our resulting histogram. Very, very easy. Once you have something like that, you can actually double click on this, and it's going to open an editor where you can then subsequently go in and edit the histogram as you'd like. Because of course the way it outputs by default is usually not, it's not publication ready, so you might have to do some additional tinkering around with that sort of thing, but it's generally not that difficult. I'll do a quick box plot. So back to Graphs, Chart Builder. So I'm going to select box plots, take the first one, drag it, sets it up again. And so this time I'm going to put, say, blood pressure on the y-axis. So that's our continuous variable of interest. And I'll categorize BMI on the horizontal axis. So sets everything up automatically. I just press OK to run the function. And there's our box plot, our blood pressure as a function of categorized BMI. As you can see in this case, what we didn't see before is we have a few outliers represented as individual points outside of the box plots. And one last thing I'll do is a scatter plot. So if I look at Chart Builder again, just going to get rid of my variables. So I click on scatter/dot, and again, I'm going to choose the first one and just drag it onto the screen. And so let's look at, I don't know, tricep skin fold thickness on the horizontal and blood pressure again on the vertical. Run the function, and we get our scatter plot of these two variables. And then if you wanted to fit like a best fit line to this data, again, you just double click to open up the chart builder, and there's a button you can click on that just says add fit line at total, and that's automatically just going to put your best fit line onto that plot.
Can I ask a question on that?
Sure.
So what if I wanted to layer on in there, let's say you had males and females. Can you discern, are all the males on top and all the females on bottom, or is there no distribution? Or
Yeah, let's see if I can remember how to do this. There is a way to do this.
even for later? If you
Yeah,
want to
even
look
for
it
later.
up.
Yeah. So SPSS isn't something that I usually use very often, but oh yeah, okay, so there's a second type of scatter plot here that I just dragged onto that working area. And I think if I go to this box set color and I choose male and female, I guess in this case I don't have male and female, I only have women, but let's say I do BMI again. I think this is what I want. Let's just see. Yeah, there you go. Yeah. So yeah, as you can see, doing all these functions is actually quite easy. The difficult part is really just getting your data into a nice, clean format. Okay, so that's all I have for our tutorial. So any questions on the tutorial?
Hello.
Hi.
Could you give us more examples of possible assumptions we could be making that we're not aware of?
Well, the standard one is assuming a normal distribution. Like if you look at many statistical tests, like the t-test, we assume that our data come from a normal distribution, which is in many cases not necessarily the case. Though as it turns out in a t-test, you can kind of get around that when you have a large sample size. Another one is when we go into linear regression. This one's a little bit harder to describe in the abstract, but an assumption that you make is that over all the values of the variable that you have on the horizontal axis, that you have kind of a constant variance on the variable on the y-axis. So if that variance is changing as you go over different values of the variable on the horizontal axis, then that can actually kind of screw up your what we call the standard error of your estimates, and it can make it seem as if your estimates are significant when they are in fact not significant. So yeah, there's two examples there that I can think of off the top of my head. Yeah.
Can I ask one more question?
Sure.
I know this more applies to a t-test, but just in the things you do before a t-test, it usually asks you between two populations if the distribution is similar. Is that true? Or am I misspeaking?
Yes, so I guess with a t-test, the main thing is the variance. So with a standard t-test, you assume that the variance in the two groups that you're studying is equal in both cases. But in fact, there is a type of t-test where that doesn't have to be true.
Great.
Yeah.
I'm asking more technically because if I can get specific and applied, if I have a cell line where a protein's overexpressed in one and then I have a control in the other, how would I look at whether the distribution is similar or not?
So that really depends. There are definitely measures for comparing different distributions. There's one called the Kolmogorov-Smirnov, which I've used a lot. There's another one, I can't remember what it's called. A lot of these tend to be a little bit more math heavy because you're considering an entire distribution instead of just like a mean or a median.
If I graph a histogram of both or look at the standard deviation or things like that, is there any things I should be looking for where I'm sure that they're not the same? That's
really dependent on what variable you're looking at. So that's almost getting into domain knowledge, I would say. So it's hard for me to say right now whether or not you should be looking at this or that.
Okay.
Yeah.
Thank you.
And yes, we'll let you know when this is ready to be posted. And we'll see you next Monday. Thank you.